For most of human history, the stars were fixed points on a crystal sphere around us. This video explores 25 discoveries that forever changed our view of the universe, revealing how each breakthrough tore down an old certainty and rebuilt our reality on a grander scale. You will gain a complete narrative of cosmic enlightenment, from learning we are not the center to hearing the echoes of colliding black holes. How did a faint static hiss become proof of the universe's violent birth? And what invisible substance holds galaxies together? Which single idea made you question your place in the cosmos? That first discovery arrived not with a telescope, but with a quiet mathematical argument. In the year 1543, as a book titled On the Revolutions of the Heavenly Spheres was placed into the hands of its dying author, Nicolaus Copernicus, our entire cosmic address was rewritten. For over 1,000 years, the dominant view, perfected by the ancient astronomer Ptolemy, placed a stationary Earth at the center of everything. The sun, the moon, the planets, and the stars all revolved around us in a complex dance of circles within circles, an intricate model built to explain the peculiar loops planets seemed to trace in the night sky. Copernicus looked at that same sky and saw an unnecessary complication. He proposed a stunningly simple, yet profoundly unsettling alternative. What if the sun was at the center and Earth was just another planet, the third one out, spinning on its axis and orbiting annually like all the others? This heliocentric model did not just move a dot on a diagram, it moved us. Humanity was physically relocated from the privileged center of creation to a rocky ball hurtling through space. The psychological impact was seismic. It challenged not only ancient science but deeply held philosophical and religious beliefs about humanity's unique place in the cosmos. Yet, the evidence was in the math. Copernicus's sun-centered system elegantly explained the puzzling retrograde motion of planets like Mars. That apparent backward loop in the sky was not the planet itself reversing course, but simply our faster-moving Earth overtaking it on the inside orbital track, a perspective shift we now understand perfectly when driving past a slower car on the highway. Astronomer Carl Sagan later reflected that it is far better to grasp the universe as it really is than to persist in a comforting delusion. Copernicus offered that first, cold, magnificent glimpse of reality. His work established a crucial framework, a universe operating by consistent, discoverable laws, setting the stage for the next genius who would ask, if the planets are moving, what invisible hand is guiding their paths? Copernicus had given us a new map of the solar system, but the rules of the road were still a mystery. Planets did not glide in serene, perfect circles as the ancients believed. They sped up and slowed down in a silent, complex rhythm. It would take the mind of a mystic mathematician, Johannes Kepler, and the obsessive records of a nobleman with a metal nose to finally hear the music. That nobleman was Tycho Brahe, the last great naked-eye astronomer, who spent decades measuring the positions of stars and planets with unprecedented precision, building a treasure trove of data without a single telescope. Upon Tycho's passing, this priceless inheritance fell to his assistant, Kepler. Kepler was a man driven by a profound belief that the universe was built on geometric harmony. He spent years trying to force Tycho's observations of Mars to fit into the old model of circular orbits, but the numbers simply would not cooperate. The planet's path stubbornly refused to be a circle. This was the pivotal moment. Instead of dismissing the data, Kepler dismissed 2,000 years of philosophical dogma. He abandoned the circle. What if planetary orbits were a different, slightly squashed shape? The answer was the ellipse. Kepler's first law was a quiet revolution. Every planet orbits the sun in an ellipse, with the sun not at the center, but at one of the two focal points. This single idea shattered the ancient ideal of heavenly perfection. The universe was not built on flawless circles, but on a slightly off-centered geometry that perfectly matched reality. But Kepler did not stop there. His genius was in seeing the motion within the shape. His second law revealed the tempo of the orbital dance. A planet does not move at a constant speed. It sweeps out equal areas in equal times. Imagine a line connecting the planet to the Sun. As the planet moves closer to the Sun in its elliptical path, that line has to cover the same area in the same amount of time as when it is far away. To do that, the planet must speed up. It races through the perihelion, its closest approach, and slows to a crawl at the aphelion, its farthest point. Finally, Kepler's third law provided a cosmic harmony, a mathematical relationship that linked the entire solar system together. He found that the square of a planet's orbital period, the time it takes to go around the Sun once, is proportional to the cube of its average distance from the Sun. This was not just a description, it was a predictive rule. If you know how far a planet is from the Sun, you can calculate precisely how long its year will be. These three laws transformed the heavens from a realm of mystical wanderers into a precise, predictable clockwork. They gave astronomy its first true mathematical foundation. Now, with the celestial mechanics laid bare, a towering question remained. What invisible force, what cosmic hand, was pushing and pulling these worlds along their elliptical paths, governing their speed with such perfect, predictable regularity? The stage was set for a mind that could explain not just how the planets moved, but why. Kepler had given us the music of the spheres, but the composer remained hidden. What invisible hand conducted this grand orbital symphony? The answer came not from a mountaintop observatory, but from a quiet English garden with a falling apple as its unlikely muse. Isaac Newton, in a moment of profound insight, saw a deep connection between the mundane and the celestial. The same force that pulled the apple from the tree to the ground must also extend its reach, diminishing but never vanishing, all the way to the moon. He realized gravity was not a property unique to Earth, but a universal force of attraction between all objects with mass. His law of universal gravitation was breathtaking in its simplicity and power. Every particle of matter attracts every other particle with a force that depends on just two things: the product of their masses and the square of the distance between them. This is the inverse square law, a mathematical rule stating that if you double the distance between two objects, the gravitational pull between them weakens to just 1/4 of its original strength. This single equation, published in his monumental work Philosophiae Naturalis Principia Mathematica, unified the cosmos. It explained why apples fall and why planets orbit. It proved that the same physical laws governing a rolling cart on Earth also governed the majestic dance of Jupiter and its moons. For the first time, celestial mechanics was no longer mystical, it was predictable. Using Newton's equations, astronomers could not only chart the known planets with stunning accuracy, they could predict the existence of unseen worlds. When the orbit of Uranus showed a slight, unexplained wobble in the 19th century, mathematicians used Newton's laws to calculate the precise location of an unseen gravitational tug. They pointed their telescopes, and there it was, the ice giant Neptune, a planet discovered at the tip of a pen before it was seen through a lens. This was the ultimate triumph of a universe governed by discoverable, immutable laws. It meant the cosmos was rational, comprehensible, and subject to human calculation. For centuries, this framework seemed complete. But what does it truly mean that the same gentle force that holds your feet to the ground also binds stars into galaxies and galaxies into clusters? It means we are woven into the fabric of the universe by the most fundamental of threads. Yet, as powerful as Newton's vision was, it would eventually meet its limits. When dealing with the crushing gravity of a collapsed star or the incomprehensible speed of light itself, the elegant clockwork universe began to show subtle cracks. waiting for a new mind to see a deeper, stranger reality. Newton's clockwork universe was vast, but it still had walls. For centuries, astronomers gazing at faint, fuzzy patches of light in the night sky called them nebulae, assuming they were swirling clouds of gas and dust nestled safely within the comforting boundaries of our own Milky Way galaxy. Our galaxy was the entire universe. That profound, insulating belief was shattered not by a complex theory, but by a single, brilliant observation on a cold Mount Wilson night. Edwin Hubble, peering through the massive 100-inch Hooker telescope, the most powerful in the world at the time, focused on a particular spiral nebula, the one we call Andromeda. His target was not the nebula itself, but a special kind of stellar lighthouse blinking within it, a Cepheid variable star. These stars are cosmic yardsticks. Their intrinsic brightness is directly linked to the rhythm of their pulse, the time it takes them to brighten and dim. By measuring this period, astronomers can calculate the star's true luminosity. Then, by comparing that true brightness to how faint it appears from Earth, you can determine its distance with remarkable accuracy. It is like knowing the exact wattage of a light bulb, and then seeing how dim it looks from far away to judge how many miles you are from it. When Hubble applied this method to the Cepheid he found in Andromeda, the number was staggering. The calculation placed Andromeda nearly 1 million light-years away, a distance so immense it could not possibly reside within the Milky Way. That faint smudge was not a cloud in our backyard. It was an entire island universe of its own, a colossal city of stars separated from us by a vast ocean of empty space. In an instant, the cosmos expanded exponentially. The Milky Way was demoted from being the universe to being one galaxy among what we now know to be hundreds of billions. Hubble himself captured the spirit of this leap, saying, equipped with his 5 senses, man explores the universe around him and calls the adventure science. This was perhaps the greatest adventure yet, a redefinition of home on a scale that dwarfed even the Copernican Revolution. But with this breathtaking new map came an immediate and puzzling question. If the universe is now filled with these island galaxies, how are they arranged, and more curiously, are they standing still? When Hubble and others began to measure the light from these distant galaxies, they noticed something peculiar, a subtle shift in the color of their starlight that would whisper a secret far more startling than the mere existence of galaxies themselves. The color of a galaxy's light held a secret, and it was written in a code of stretching wavelengths. While Hubble had proven galaxies existed beyond our own, another astronomer, Vesto Slipher, had been patiently collecting their spectral fingerprints. He noticed a strange pattern. For almost every galaxy he observed, the familiar signature of elements like hydrogen and helium was not where it should be. The lines were shifted toward the red end of the spectrum. This redshift was a cosmic Doppler effect, the same phenomenon that makes a siren's pitch drop as the ambulance speeds away from you. The light waves from these galaxies were being stretched as they traveled through space to reach us. The unavoidable conclusion was that nearly all galaxies were racing away from our own. Hubble took this revelation and, with his genius for measurement, added the crucial second piece. He combined Slipher's redshift data with his own hard-won distances to those galaxies. The correlation he found was simple, direct, and utterly world-shaking. The farther away a galaxy is, the faster it appears to be receding from us. This relationship, now called Hubble's law, was not just a description of motion. It was a snapshot of the universe's fundamental behavior. Space itself was not static, it was actively growing, stretching the very fabric between galaxies. A helpful analogy is to think of raisins baked into a loaf of rising bread dough. As the dough expands uniformly, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding, and the ones farther away appear to move faster because there is more expanding dough between them. We are not at the center of this expansion any more than one raisin is the center of the loaf. From every point in the universe, the view would look the same, a grand, uniform stretching of space on the largest scales. This single observation changed everything. A static, eternal cosmos was gone, replaced by a dynamic, evolving entity with a history. If the universe is expanding now, then running the cosmic film backward in time implies a moment when everything we see, all matter and energy, was compressed into an unimaginably hot, dense state. The expanding universe pointed directly to a finite beginning, a moment of origin we now call the Big Bang. This shifted cosmology from a study of fixed structures to a search for a cosmic origin story, forcing a profound reconciliation between scientific evidence and age-old philosophical questions about creation. It meant the universe had a birthday, but if there was a beginning, what tangible evidence could possibly remain from that first fiery moment? The answer would come not from a telescope pointed at distant stars, but from a humble antenna scanning the empty static between them. Sometimes the greatest discoveries begin with a persistent annoyance. In the mid-1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to calibrate a massive, ultra-sensitive horn antenna originally built for satellite communication. But no matter where they pointed it, they were plagued by a faint, unshakable hiss, a uniform microwave static that seemed to come from every direction in the sky. They checked everything. They chased pigeons out of the antenna and scrubbed away what they called a white dielectric material, but the whisper remained. This was not a malfunction, it was a signal from the edge of time itself. Unbeknownst to them, a team of physicists at nearby Princeton University, led by Robert Dick, had been actively searching for precisely this phenomenon. They were looking for the cooled remnant of the universe's fiery birth, the predicted afterglow of the Big Bang. When Penzias and Wilson contacted them, the pieces clicked into place. That omnipresent hiss was the cosmic microwave background radiation, the oldest light in the universe. It is the cooled and stretched echo of a time, roughly 380,000 years after the initial expansion, when the cosmos had finally cooled enough for protons and electrons to combine into neutral hydrogen atoms. In that moment, the fog cleared. Light, which had been trapped, bouncing endlessly in a hot, dense plasma, was suddenly set free to travel across the universe. That first flash of liberation has been traveling for over 13 billion years, stretched by the relentless expansion of space from visible light into the microwave part of the spectrum, cooling to a mere 2.7 degrees above absolute zero. Its discovery was the smoking gun that decisively ended the great cosmological debate between the Big Bang theory and its main rival, the steady-state model, which proposed a universe with no beginning, constantly creating new matter to maintain a constant density. The steady state could not explain this pervasive, cool background radiation. The Big Bang predicted it perfectly. The universe had a definitive hot beginning, and we could hear its fading whisper. But this was just the start. If this ancient light was a perfect, uniform blanket, our universe today would be a featureless sea of particles. We exist because it was not perfectly smooth. The quest then became to examine this baby picture of the cosmos for its faintest imperfections, the subtle wrinkles that held the blueprint for everything to come. The cosmic microwave background was a nearly perfect whisper, but perfection would have left us in a void of our own making. The universe we see is rich with structure, from delicate spiral galaxies to vast clusters, and that structure required a seed. Those seeds were found as tiny, almost imperceptible variations in the ancient light, temperature fluctuations of just 1 part in 100,000. These are the cosmic wrinkles, the places where gravity had a slightly stronger foothold. Over billions of years, these microscopic density variations grew, pulling in more and more matter, eventually giving birth to the first stars and the grand architecture of galaxies. This was the story of how visible matter built the cosmos. But when astronomers like Vera Rubin and Kent Ford began to measure how those galaxies actually moved, the story fell completely apart. Rubin, using meticulous observations, mapped the rotation of spiral galaxies. According to Newton's laws, stars orbiting a galactic center should behave like planets in a solar system. Those farther out from the center, where the visible mass of stars and gas thins out, should orbit more slowly. Imagine a child on a merry-go-round. The closer they are to the center, the slower they need to move to complete a circle. The child on the outer edge has to run much faster. Rubin expected to see the stars at the outer edges of galaxies slowing down. What she and Ford found was astonishing. The stars far from the galactic center were not slowing down at all. They were orbiting just as fast as the stars near the bright core. This meant the gravitational glue holding these fast-moving outer stars in place was far stronger than the pull from all the visible stars, gas, and dust we could see. The only possible explanation was that galaxies were embedded within enormous, invisible halos of something else, a form of matter that exerted gravity but emitted no light. We call this missing component dark matter. It does not shine, absorb, or reflect light. We cannot see it with any telescope because it interacts with light only by bending its path through the immense distortion of gravity, an effect called gravitational lensing. We see this when the gravity of a massive galaxy cluster acts as a cosmic magnifying glass, warping and distorting the light from galaxies far behind it. The amount of distortion reveals that there is far more mass present than the glowing galaxies show. This invisible matter also provides the essential scaffolding for the universe's large-scale structure, the great cosmic web of filaments and voids that defines the distribution of galaxies. Without the gravitational anchor of dark matter, ordinary matter would have been too diffuse and moving too quickly after the Big Bang to ever clump together into the galaxies we see today. So what is it? The leading idea suggests weakly interacting massive particles, or WIMP, hypothetical particles that barely interact with normal matter except through gravity and perhaps the weak nuclear force. Other candidates include theoretical particles called actions. Despite decades of searching in underground laboratories and with particle colliders, dark matter's exact identity remains one of the greatest unsolved puzzles in physics. We know it is real, we can map its distribution by its gravitational effects, and we know it constitutes about 27% of the total mass energy content of the cosmos. That means over 80% of all matter in the universe is of a form we cannot see. How does it feel to know the grand spiral of a galaxy, a beacon of light in the void, is just a decorative pattern etched onto a vast, invisible framework? This unseen architecture holds the universe together. Yet, as the 20th century drew to a close, astronomers made a discovery about the cosmos that suggested an invisible force was not just holding things together, but actively and mysteriously tearing them apart. If dark matter was the universe's hidden scaffolding, a second, even stranger component was about to rewrite its future. For decades after Hubble's discovery, cosmologists assumed the expansion of the universe was a story of gradual slowdown. The mutual gravitational attraction of all the galaxies, clusters, and dark matter should act like a cosmic brake, gradually pulling on the fabric of space and decelerating the great outward rush. The central question was simply how much it was slowing, and whether there was enough matter to one day halt the expansion entirely, leading to a potential big crunch. To measure this cosmic deceleration, two independent teams set out in the late 1990s to use a special kind of stellar explosion as a standard candle, a Type 1, a supernova. These are the brilliant, predictable detonations of white dwarf stars, and by measuring how bright they appear from Earth, astronomers can calculate their distance with incredible precision. At the same time, by measuring the redshift of their host galaxies, they know how much the universe has stretched since the light left the explosion. By comparing supernovae from different distances, and therefore different eras in cosmic history, they could chart how the expansion rate has changed over billions of years. The results were not just surprising, they were paradigm-shattering. The most distant supernova, whose light had been traveling for billions of years, were fainter than expected. This meant they were farther away than a steadily decelerating universe would predict. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart at an ever-increasing rate. This force was named dark energy. It is not a substance like dark matter, but rather a property of space itself. Empty space, according to this revelation, is not nothing. It possesses a latent energy, a kind of anti-gravity that causes the very fabric of the cosmos to stretch faster as more space comes into existence. This idea was not entirely new. Albert Einstein had introduced a similar concept a century earlier, called the cosmological constant, a mathematical fudge factor he added to his equations of general relativity to force a static, unchanging universe. He later called it his greatest blunder when Hubble proved the universe was expanding. It turns out his blunder may have been a stroke of genius, just applied to the wrong problem. The cosmological constant is the leading candidate for what dark energy might be, a constant energy density inherent to the vacuum of space. The numbers are staggering. Our best measurements tell us that all the stars, galaxies, planets, gas, dust, and even all the invisible dark matter combined make up only about 32% of the total cosmic pie. Dark energy, this enigmatic push of empty space, constitutes the remaining 68%. It is the dominant component of our universe. This discovery completely overturned our long-term forecast for the cosmos. Instead of a potential future collapse, we now envision a cold, lonely end. As dark energy continues to drive the acceleration, galaxies beyond our local group will eventually recede so fast that their light can no longer reach us. The observable universe will shrink. Distant civilizations of the far future will look out and see only their own galaxy in a vast, empty blackness, with no evidence of a Big Bang or an expanding cosmos at all. What does it mean that the void itself is the most powerful actor in the cosmic drama? It means the fate of everything is tied to the nature of nothing. With our modern inventory of the cosmos now complete, a profound question arises. How do we begin to make sense of a universe where 95% of its content is utterly invisible and unknown? Newton's elegant clockwork had a hidden flaw, a subtle mismatch between its predictions and the observed motion of Mercury, the innermost planet. Its orbit was slowly rotating, a tiny drift that could not be explained by the gravity of the Sun and the known planets alone. This was the puzzle Albert Einstein solved, not by adding another gear to the cosmic machine, but by dismantling the machine entirely and rebuilding reality from the ground up. In his theory of general relativity, published in 1915, gravity is not a mysterious force reaching across space. It is geometry. Einstein proposed that mass and energy do not simply exist within space and time, they shape the very fabric of it. Imagine a taut rubber sheet representing the fabric of spacetime. Place a heavy bowling ball in the center. The sheet warps, creating a deep well. Now roll a marble across the sheet. It will not travel in a straight line but will curve inward, tracing an orbit around the bowling ball. The marble is not being pulled by a force, it is simply following the curved path of the sheet. This is the essence of general relativity. The Sun creates a curvature in spacetime, and planets like Earth follow the straightest possible paths called geodesics through that curved geometry. This single, breathtaking idea explained Mercury's anomalous orbit perfectly. The planet's path was not a flaw, but a precise confirmation that spacetime near the massive Sun is subtly warped. But Einstein's theory made even bolder predictions. If mass curves spacetime, then it should bend the path of light itself, which always follows the shortest path through the curved geometry. During a total solar eclipse in 1919, astronomer Arthur Eddington led an expedition to measure the positions of stars appearing near the darkened sun. The starlight passing close to the sun's immense gravity was bent. The stars appeared slightly shifted from their usual positions, exactly as Einstein's equations predicted. This confirmation made headlines worldwide, catapulting Einstein to global fame and cementing general relativity as the new law of gravity. The theory also introduced the mind-bending concept of gravitational time dilation. Time itself flows slower in a stronger gravitational field. A clock at sea level, closer to Earth's mass, ticks very slightly slower than an identical clock on a mountaintop. This is not a mechanical error, it is a fundamental property of reality, verified with astonishing precision by atomic clocks on airplanes and satellites. Our Global Positioning System, GPS, must account for this relativistic time warp to provide accurate locations, a daily, practical proof of Einstein's genius. But the most extreme consequences of this geometric view were objects so bizarre they seemed like mathematical fantasies. General relativity allowed for the existence of points where spacetime curvature becomes infinite, regions of such immense density that not even light can escape their gravitational grip. We call them black holes. It also predicted that massive accelerating objects like orbiting black holes or neutron stars would create ripples in the fabric of spacetime itself, waves that would propagate outward at the speed of light. These are gravitational waves. For a century, these ideas stood as the ultimate tests of the theory, predictions so profound they seemed almost untestable. How does it feel to know that you are not being pulled downward by the Earth, but are instead sliding smoothly along a gentle curve in the invisible fabric of the cosmos? This geometric vision did not just fix a planetary orbit, it provided the only language capable of describing the universe as a whole, from its explosive birth to its ultimate fate, and set the stage for the hunt for its most dramatic predictions. A gravitational well can become so deep it forms a bottomless pit in the fabric of spacetime. General relativity predicted these cosmic traps, regions where gravity is so overpowering that the escape velocity exceeds the speed of light. Not a single photon can fight its way out. The boundary of no return is called the event horizon, a one-way membrane separating the knowable universe from the unknowable. For decades, black holes remained theoretical specters until astronomers found compelling evidence in the constellation Cygnus. There, a star named HDE 226868 orbits an invisible companion, a dark object with a mass several times that of our Sun. Intense X-rays scream into space, not from the black hole itself, but from superheated gas ripped from the star and spiraling into the abyss, a final, violent glow before vanishing forever. This system, Cygnus X1, became the first widely accepted proof that black holes are real. We now know they are common. Stellar mass black holes, the ghosts of massive stars that have collapsed under their own weight, litter our galaxy. But far more influential are the supermassive black holes, monsters weighing millions or even billions of times the mass of our Sun, lurking at the heart of nearly every large galaxy, including our own Milky Way. In 2019, the Event Horizon Telescope collaboration achieved the impossible, combining radio telescopes across the globe to create an Earth-sized instrument. Their target was the supermassive black hole at the core of galaxy M87, 55 million light-years away. The image they produced was not of the black hole itself, for it is invisible, but of its shadow, a dark silhouette encircled by a fiery ring of bent light, a perfect match to Einstein's predictions. This was humanity's first direct glimpse of the edge of infinity. These objects are not passive drains, they are the universe's most powerful engines. As matter falls in, immense magnetic fields can funnel some of it into blazing jets that shoot out for thousands of light years, regulating star formation and shaping entire galaxies. The brilliant cores of distant quasars, the most luminous objects in the cosmos, are powered by supermassive black holes in a ferocious feeding frenzy. Yet, at the very center of a black hole lies the singularity, a point of infinite density where the equations of general relativity break down and our understanding of physics ends. It is a realm where the concepts of space and time lose all meaning. For an object falling in, from our perspective, time appears to slow to a stop at the event horizon, a final, frozen moment stretched across eternity. Can you conceive of a place where time effectively stops? These gravitational paradoxes, once thought to be mathematical curiosities, are now known to be common architects of the cosmic landscape. And when two of them spiral together and collide, they do not do so silently. They shake the universe, sending out ripples in spacetime that we have only just learned to hear. The fabric of spacetime is not silent. It can ring like a bell, sending faint tremors across the cosmos when the most massive objects collide. For a century after Einstein predicted their existence, gravitational waves remained a whisper just beyond our hearing, a theoretical echo of cosmic violence. Then, on September 14, 2015, a billion-dollar instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory, finally heard it. In two identical facilities separated by nearly 2,000 miles, one in Louisiana and one in Washington state, a laser beam split and traveled down 4-kilometer-long vacuum tubes, bounced off mirrors and recombined. The design was exquisitely sensitive to a change in distance 1/10,000th the width of a proton. On that morning, both detectors registered an identical, unmistakable chirp. For a fraction of a second, the length of one arm stretched and the other compressed as a ripple in spacetime itself passed through our planet. The signal perfectly matched the prediction for two black holes, one about 36 times the mass of our Sun and the other 29, spiraling together and merging over 1 billion light-years away. In that final cataclysm, 3 solar masses worth of pure energy was converted into gravitational waves in a fraction of a second, a power output greater than all the stars in the observable universe combined. This was the first direct detection, a century after Einstein's paper, confirming one of the last great unproven predictions of general relativity. But this was more than just confirmation. It was the birth of an entirely new sense. Before this moment, astronomy was done with light, from radio waves to gamma rays. Now we could listen. Scientists translated the wave's frequency into an audible sound, a quick upward sweep from a low hum to a final chirp, the literal sound of two black holes becoming one. This new sense of hearing the universe, called multi-messenger astronomy, allows us to perceive events that are often dark to traditional telescopes. 2 years later, in August of 2017, LIGO and its European counterpart Virgo detected a different kind of tremor, the ripples from 2 neutron stars, the ultra-dense cores of dead stars colliding. This time, telescopes around the world and in space swiveled to the same patch of sky, catching the flash of light and the afterglow across the electromagnetic spectrum. This single event told a complete story, the gravitational waves revealing the masses and dance of the objects, the light revealing the creation of heavy elements like gold and platinum forged in the cosmic furnace. We learned that such collisions are likely the cosmic foundries for most of the universe's gold. To listen to gravitational waves is to hear the universe doing its most extreme work, bending and shaking the very stage upon which everything plays out. It allows us to probe gravity in its most ferocious regime and to witness the final moments of systems that emit no light at all. What other invisible symphonies are traveling through us right now, carrying stories from the edges of reality? Sometimes the universe signals us with a steady, metronomic beat. In 1967, a young doctoral student named Jocelyn Bell Burnell was analyzing data from a new radio telescope she had helped build. She noticed a peculiar, repeating signal, a sharp pulse arriving every 1.337 seconds with such perfect regularity, it seemed almost artificial. Her initial, cautious label for it was LGM-1 for Little Green Men, a nod to the possibility it was a beacon from an alien civilization. What she had actually found was far stranger than science fiction. It was a pulsar, a cosmic lighthouse of unimaginable density. A pulsar is the spinning core of a massive star that did not collapse completely into a black hole. When such a star explodes as a supernova, its outer layers are blasted away, but its core, compressed by gravity, can survive as a neutron star. This object is so dense that a single teaspoon of its material would weigh as much as a mountain. It packs more mass than our Sun into a sphere only about 12 miles across. This tiny, furious remnant spins at a breathtaking rate, and it possesses a powerful magnetic field trillions of times stronger than Earth. From the magnetic poles of this spinning cinder, focused beams of radio waves and sometimes other radiation shoot out into space. Just as a lighthouse beam sweeps across a dark sea, these beams sweep across the cosmos. When one of those beams happens to point toward Earth, our telescopes register a pulse. We are not seeing the star itself flash on and off. We are witnessing the cosmic geometry of a spinning beacon. The precision of these pulses is staggering. Some pulsars rival the best atomic clocks on Earth in their regularity, their spin slowed only minutely by the faint emission of energy. This incredible reliability makes them superb tools for navigation. Scientists have even proposed using a network of pulsars as a galactic positioning system for future spacecraft traveling between the stars. But the true power of pulsars as cosmic laboratories was revealed with the discovery of a binary system, two pulsars orbiting each other. By meticulously timing their pulses, astronomers led by Joseph Taylor and Russell Hulse could track their orbital decay. The two stars were spiraling inward, losing orbital energy at the exact rate predicted if they were radiating energy away in the form of gravitational waves. This was the first brilliant indirect proof that Einstein's ripples in spacetime were real, a discovery that earned a Nobel Prize and paved the way for direct detectors like LIGO decades later. Pulsars show us matter crushed into a state that cannot be replicated in any laboratory, where atomic nuclei are packed shoulder to shoulder. They are the precise, ticking hearts of dead stars, proving that from stellar death can come both incredible order and profound new physics. If such exotic matter exists in the cold remnants of stars, what of the ingredients for life? The next discovery would trace those very building blocks, not in the safety of a planet's surface, but in the vast, frigid emptiness between the stars. The building blocks of life are not unique to our warm, wet planet. They are woven into the cold, dark fabric of the galaxy itself. For decades, radio telescopes have been eavesdropping on the chemical conversations happening in vast interstellar clouds, like the immense Sagittarius B2 near the center of our Milky Way. These cosmic nurseries are not empty. They are rich chemical factories filled with simple molecules like carbon monoxide and hydrogen, but also, astonishingly, with complex organic compounds. Scientists have identified over 200 different molecular species in space, including alcohols, acids, and even sugars like glycolaldehyde, a simple sugar that is a component of ribonucleic acid or RNA. Perhaps the most profound discovery came from a visitor to our inner solar system. The European Space Agency's Rosetta mission followed Comet 67P, Churyumov-Gerasimenko, for years, and its lander, Philae, detected the amino acid glycine in the comet's fuzzy atmosphere and on its dusty surface. Glycine is one of the simplest amino acids, a fundamental piece used to build proteins, the workhorse molecules of all known life. This was a direct, in situ confirmation that the ingredients for biology can form in the frigid depths of space, on the icy grains of comets and asteroids. The process likely involves simple chemistry on dust particles, where radiation from nearby stars provides the energy to link atoms into ever more complex chains. When these icy bodies later fall onto young planets like the early Earth, they deliver a rich starter kit of prebiotic material. This concept that life's raw materials are a cosmic commonplace is known as the cosmic feedstock. It suggests the universe is chemically primed, even predisposed toward the chemistry of life. It also lends weight to the ancient idea of panspermia, the hypothesis that life itself, or at least its crucial precursors, could hitchhike between planetary systems on asteroids, comets, or dust, seeding life wherever it finds a welcoming environment. While we have no evidence that full living organisms made such a journey to Earth, we now know the molecular letters of life's alphabet were raining down upon our world from its very beginning. So what does this mean for you sitting here today? It means the carbon in your cells, the nitrogen in your DNA, and the oxygen you breathe were forged in the hearts of ancient stars and then assembled into life's precursors on the icy backdrop of interstellar space. Your biological lineage does not begin in a primordial pond on Earth alone. It stretches back through the comet that delivered water, through the molecular cloud that gave it structure, to the stellar explosion that created the elements themselves. If the universe is such a prolific chemist, then the transition from chemistry to biology might not be a rare miracle, but a natural, even probable, next step given the right conditions of liquid water, a stable environment, and time. This shifts the question of life elsewhere in the cosmos from one of possibility to one of expectation. The galaxy may be quietly, patiently, assembling the pieces everywhere. But for life to truly blossom, those pieces need a stable home, a stage on which the chemistry can become biology. This leads us to look beyond our solar system, to ask if other stars are also providing such stages, and to wonder if we might one day detect the faint signs of a living world light years away. For millennia, the question of other worlds was pure philosophy. Then, in October 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, made an announcement that turned philosophy into fact. They had found a planet orbiting a sun-like star called 51 Pegasi, a star visible to the naked eye. This world, 51 Pegasi b, was utterly alien to our solar system. It was a gas giant like Jupiter, but it orbited its star in a blistering 4.2 days, so close that its surface temperature would be scorching. We call such worlds hot Jupiters, and its existence shattered all our preconceived notions of how planetary systems form and behave. Our own solar system, with its small rocky worlds close to the sun and gas giants in the cold outer reaches, was not the only blueprint. It was just one possible arrangement in a galaxy of infinite variety. The method Mayor and Queloz used was the radial velocity technique, also called the Doppler wobble. It does not see the planet directly. Instead, it detects the tiny gravitational tug the planet exerts on its star. As the planet orbits, it causes the star to wobble in a small, predictable circle. When the star wobbles toward us, its light is slightly compressed, shifted toward the blue end of the spectrum. As it wobbles away, the light stretches toward red. By measuring this rhythmic color shift, astronomers can deduce the planet's minimum mass and the length of its year. This discovery flung open a door, and a flood of new worlds followed. The most prolific planet hunter became the Kepler Space Telescope, which used a different, powerful method called the transit technique. Kepler stared fixedly at one patch of sky containing over 100,000 stars, waiting for a telltale dimming. When a planet passes directly in front of its star from our line of sight, it blocks a tiny fraction of the star's light, causing a brief, periodic dip in brightness. This transit reveals the planet's size and its orbital period. Kepler's data was a revelation. It showed us that planets are not rare, they are more common than stars. The Milky Way likely contains hundreds of billions of planets. We found systems with multiple worlds packed into orbits smaller than Mercury's, planets orbiting binary stars like the fictional Tatooine, and miniature versions of Neptune zipping around their stars in hours. The architecture of our own solar system, it turns out, is the exception, not the rule. The torch has now been passed to missions like TESS, the Transiting Exoplanet Survey satellite, which is scanning nearly the entire sky for planets around the brightest nearby stars, building a catalogue of the best targets for the next critical step. The ultimate goal is no longer just finding planets, but studying their atmospheres. When a planet transits its star, a sliver of starlight filters through its atmosphere. Different molecules in that atmosphere absorb specific colors of light, leaving a chemical fingerprint in the starlight. With powerful telescopes like the James Webb Space Telescope, we are beginning to read these fingerprints, searching for gases like oxygen, methane, and water vapor that, in certain combinations, could be potential biosignatures, signs of biological activity. The discovery of exoplanets has fundamentally changed the equation of life in the universe. We now know the galaxy provides an almost unimaginable number of stages. The question has shifted from a speculative, are there other worlds, to a practical, which of these countless worlds shows signs of a living, breathing biosphere. We are no longer wondering if we are alone. We are beginning to learn how to listen for the whispers of our cosmic neighbors. Yet, to understand what makes a world truly habitable, we must first look closely at the one example we have, to see it not as a singular home, but as a dynamic system of interconnected forces. Our own planet is a masterpiece of restless geology, but for centuries its siblings in the solar system were just pale dots or colored disks, assumed to be frozen in time. That illusion of stillness was shattered by the robotic emissaries we sent on grand tours. The twin Voyager probes, swinging past Jupiter and Saturn in the late 1970s, sent back the first jaw-dropping evidence. At Jupiter, they found a moon named Io, a world painted in garish yellows and oranges, not by alien vegetation, but by ceaseless volcanic fury. Io is the most volcanically active body in the solar system, its surface constantly remodeled by hundreds of erupting vents, spewing sulfur and silicate lava hundreds of miles into space. This hellish activity is not powered by a molten core like Earth's, but by the relentless gravitational kneading of Jupiter and its other large moons. The same gravitational forces, called tidal heating, work a different magic on the next moon out, Europa. Voyager's images showed a cracked, icy shell crisscrossed with dark lines, a surface that looked like a cracked eggshell floating in space. This hinted at something profound beneath the ice. Later, the Galileo orbiter confirmed it. Europa hides a global saltwater ocean, containing perhaps twice the liquid water of all Earth's oceans combined, kept warm and liquid by that same tidal friction. The concept of a habitable world exploded. A planet did not need to orbit within the narrow Goldilocks zone where liquid water can exist on the surface. A world could be an ice-covered ocean heated from within. This revelation was underscored spectacularly at Saturn by the Cassini mission. The small, bright moon Enceladus, just over 300 miles across, was found to be geologically alive. Cassini discovered enormous plumes of water vapor and ice crystals erupting from tiger stripe fractures near its south pole, shooting hundreds of miles into space. The spacecraft flew directly through these plumes, analyzing their composition and finding they contained simple organic molecules and salts, the chemical ingredients and energy sources that could potentially support microbial life. Even more astonishing was Saturn's largest moon, Titan. Hidden beneath a thick, orange haze, Cassini's radar and the Huygens lander revealed a landscape hauntingly familiar, yet utterly alien. Here, rivers and lakes exist, but they are not filled with water. They are pools of liquid methane and ethane, hydrocarbons that flow and evaporate in a complex meteorological cycle at nearly 300 degrees below zero. Titan has rain, valleys, dunes, and even evidence of cryovolcanoes that might spew a chilly slurry of water and ammonia. These discoveries showed that Earth-like processes, volcanism, tectonics, erosion, and fluid cycles are not unique. They are universal tools that shape worlds, even when the materials and temperatures are wildly different. And then there is Mars. While its surface is now a cold, dry desert, orbiters and rovers have mapped unmistakable signs of a warmer, wetter past, vast networks of dried river valleys, enormous flood channels, and mineral deposits that only form in the presence of liquid water. This evidence of ancient Martian rivers and lakes tells us that the conditions suitable for life, as we understand it, once existed beyond Earth. So, could life exist in the dark, sunless ocean beneath Europa's ice, or in the hydrothermal vents on the floor of Enceladus's sea? The possibility is no longer science fiction. These active, dynamic worlds have rewritten the checklist for habitability. We must now look for life not just on Earth like planets, but in the subsurface oceans of icy moons, in the methane rivers of Titan, and anywhere chemistry, energy, and a stable liquid medium can persist over geologic time. The search for our cosmic neighbors just became vastly more interesting because they may not be living on a planet's surface at all, but swimming in the eternal night of a hidden sea. A single dark speck of our sky is not empty. It is a window into the deep past. In December 1995, astronomers took an audacious gamble with the newly repaired Hubble Space Telescope. They pointed its delicate instruments at a tiny, seemingly blank patch of sky near the Big Dipper, an area so small it would be covered by a grain of sand held at arm's length. For 10 consecutive days, over 100 hours in total, Hubble gathered every precious photon it could, staring into the void. The resulting image, the Hubble Deep Field, did not show emptiness. It revealed a universe teeming with light. That single frame contained over 3,000 galaxies, each a sprawling island of billions of stars in every conceivable shape and stage of life. Some were majestic spirals, others were fuzzy ellipticals, and many were mere smudges of red light, the infant galaxies of the early cosmos. This was not just a photograph, it was a core sample drilled into the fabric of space and time. By looking far away, Hubble was looking back in time, capturing light that had been traveling for over 12 billion years. Subsequent observations, like the Hubble Ultra Deep Field, pushed this view to within a mere 500 million years of the Big Bang, capturing the faint, red glow of the universe's first galactic building blocks. The visual impact was immediate and humbling. The abstract numbers of cosmology, billions of galaxies, trillions of stars, suddenly became a tangible, crowded reality. If such a profusion of worlds existed in a random pinprick of our sky, then the observable universe must contain hundreds of billions of galaxies. This single image made the cosmic vastness inescapably real. It showed us the universe's rich history written in light, a fossil record of galactic evolution from clumsy infancy to grand maturity. That tiny dark patch was a universe in a teaspoon. To see it is to understand that every direction we look is filled with the same unimaginable depth, a lesson in both our profound smallness and our incredible privilege of sight. What does it mean that our most powerful telescope, by staring at nothing, revealed everything? It means the cosmos is a story waiting in every direction, and we have only just begun to read the first page. With this map of the ancient universe in hand, the next question was inevitable. How did these first, faint smudges of light grow into the grand structures we see today? We can now measure the birthday of everything by combining the most precise observations of the cosmic microwave background, the distant supernova that revealed dark energy, and the vast maps of galaxy clusters, cosmologists have assembled a detailed cosmic timeline. The universe is approximately 13.8 billion years old. That number is not a rough estimate. It is a highly constrained figure derived from the subtle patterns in the ancient light, the rate of expansion, and the amount of visible and dark matter. This timeline gives us a coherent narrative, a story with chapters. In the first few minutes, the universe was a seething nuclear furnace, forging the lightest elements, hydrogen and helium, with traces of lithium. For hundreds of millions of years, it was a dark, expanding sea of gas, until gravity's patient work coalesced the first stars, whose brilliant lives and violent deaths then seeded the cosmos with heavier elements like carbon, oxygen, and iron. Galaxies assembled, merged, and grew, their central black holes flaring to life. Our solar system condensed from the recycled debris of earlier stellar generations a mere 4.6 billion years ago, a recent event in this grand chronicle. This framework reveals our cosmic epoch. We live in the stelliferous era, the age of stars, but we have arrived late in the party. The most prolific period of star formation is long past, and the universe, dominated by dark energy, is now in an era of accelerated expansion. This leads to a forecast for the ultimate fate, often called the heat death or the big freeze. As expansion continues to accelerate, galaxies beyond our local group will fade from view. Stars will eventually burn through their fuel, novas will fade, and black holes will slowly evaporate over incomprehensible timescales. The universe will trend toward a state of maximum entropy, a uniform, cold, and dilute sea of particles where no more work can be done and no new structures form. It is an end not of fire but of profound and endless quiet. To stand within this timeline is an exercise in radical perspective. All of recorded human history, every empire, every discovery, every life lived, occupies less than a blink in this cosmic year. Our entire species has existed for a fraction of a final second on this scale. This is not a lesson in insignificance, but in precious rarity. We are the universe made from its ancient elements, become conscious and able to trace its own story back to the first moment. Our fleeting awareness is the cosmos understanding itself, and if we can pinpoint the beginning with such precision, it forces a profound question. What could possibly have happened in the very first fraction of a second, when all the energy of the cosmos was compressed into a space smaller than a single atom? The smooth, uniform whisper of the cosmic microwave background presented a profound puzzle. How could regions of the universe on opposite sides of the sky, regions that could not have exchanged a single photon since the beginning of time, be at nearly the exact same temperature? This is the horizon problem. Furthermore, measurements showed the geometry of our universe to be remarkably flat, a delicate balancing act that seemed too perfect to be an accident. In the early 1980s, a young physicist named Alan Guth proposed a breathtaking solution, a cosmic plot twist in the very first moments of everything. He called it inflation. The theory suggests that a fraction of a second after the Big Bang, perhaps around 10 to the power of -36 seconds, the universe was seized by a repulsive energy inherent to space itself, a primordial version of dark energy but unimaginably more potent. This energy caused the fabric of spacetime to expand at an exponential, faster-than-light rate, doubling in size repeatedly in intervals so brief they are almost meaningless to describe. In that fleeting instant, a subatomic speck of the primordial universe was blown up to a size larger than our entire observable cosmos today. This explains the horizon problem because everything we see was once crammed into a tiny, causally connected region that was then stretched to cosmic proportions, preserving its uniform temperature. It also explains the flatness. Imagine inflating a balloon to an enormous size. Any tiny wrinkle or curve on its surface when it was small becomes imperceptibly smooth. Inflation stretched the geometry of the universe to such an extent that it appears flat to our measurements, just as the surface of the Earth feels flat beneath our feet. But inflation's greatest gift was providing the seeds for all future structure. At the quantum level, empty space is not truly empty. It is a seething foam of virtual particles flickering in and out of existence. Inflation stretched these quantum fluctuations from the microscopic to the macroscopic, imprinting them as tiny differences in density across the newly expanded cosmos. These are the very wrinkles we later detected in the cosmic microwave background, the gravitational seeds that, over billions of years, grew into galaxies, stars, and planets. Without inflation, our universe might have remained a featureless, uniform soup. The theory's predictions for the specific pattern of those fluctuations have been spectacularly confirmed by satellites studying the ancient light. Yet inflation leads to a staggering, almost ungraspable implication. If this exponential expansion can happen once, triggered by a certain energy state, why could it not happen elsewhere or at other times? The theory suggests that our entire observable universe, everything we can possibly see, is just one bubble in a frothing, eternally expanding cosmic foam, a multiverse. In this picture, other bubbles with entirely different physical laws and constants may be constantly budding off from an eternally inflating background. This pushes our questions about origins to an even more profound edge. Asking what happened before the Big Bang might be like a fish in a pond asking what existed before the pond. There may be no meaningful before for our bubble, only an endless, generative sea of spacetime where beginnings are local events. So, are we living in just one cosmic bubble among an infinite froth of other realities, forever separated from us by horizons of inflating space? This idea stretches the fabric of our understanding as violently as inflation stretched the infant universe, leaving us to wonder if the ultimate nature of reality is not a single story, but an endless library of possibilities. The rules governing galaxies and stars are written in the language of the impossibly small. To understand the universe at its grandest scales, we must first decipher the code of its fundamental building blocks. This is the domain of the Standard Model of particle physics, a triumph of human intellect that catalogues the ultimate ingredients of visible reality. It is a periodic table for the subatomic world, describing a zoo of particles and 3 of the 4 fundamental forces that orchestrate their interactions. There are quarks which combine in trios to form protons and neutrons. There are leptons like the familiar electron and the elusive neutrino. And there are force carrier particles like the photon that carries light and the gluon that binds atomic nuclei together. For decades, this model made stunningly accurate predictions, but it had a glaring hole. Its equations beautifully described how particles interacted, but they could not explain why most of them had any mass at all. Without mass, particles would zip around at the speed of light, and atoms, planets, and people could never form. The answer arrived in a monumental collision of data and theory. In 2012, after a decades-long hunt, scientists at the CERN laboratory announced the discovery of the Higgs boson using the Large Hadron Collider. This particle is the signature of an invisible energy field that permeates all of space, the Higgs field. Think of it like a cosmic molasses. Particles that interact strongly with this field, like quarks and electrons, move through it with difficulty, acquiring what we perceive as mass. Particles like photons, which do not interact with it, remain massless and travel at light speed. With this discovery, the Standard Model was complete. It is a framework of breathtaking power, capable of describing the behavior of matter and energy under all but the most extreme conditions. It tells the story of the universe's first moments, when temperatures were so high that these fundamental forces were unified. As the cosmos expanded and cooled, the forces separated and quarks froze into protons and neutrons. Within the first 20 minutes, during a process called Big Bang nucleosynthesis, these particles fuse to form the first atomic nuclei, primarily hydrogen and helium. The Standard Model precisely predicts the abundance of these light elements we still see today, a direct link between the physics of the subatomic and the composition of the entire cosmos. Yet, for all its success, this model presents a humbling census. All the particles it describes, everything that makes up stars, planets, and living beings, constitute less than 5% of the total content of the universe. The Standard Model has nothing to say about the dark matter that binds galaxies or the dark energy that drives cosmic expansion. It also cannot reconcile its quantum rules with Einstein's theory of gravity. This magnificent edifice, therefore, is not the final theory. It is a brilliantly successful chapter, but the book of the universe has many pages left to read. Its very incompleteness is a beacon guiding us toward the next frontier of physics. The most elusive witnesses to cosmic violence are not seen or heard, but felt as the faintest of touches. They are neutrinos, subatomic phantoms produced in staggering numbers by nuclear reactions, from our own sun to the cataclysmic deaths of distant stars. For decades, we knew they existed, but catching one from beyond our solar system seemed nearly impossible. A neutrino has no electric charge and almost no mass, allowing it to sail through entire planets as if they were made of mist. Trillions pass through your body every second, leaving no trace. To catch even a few of these cosmic ghosts requires monumental ingenuity, turning massive volumes of the Earth itself into a detector. In February 1987, such an effort paid off with a historic flash. When a star went supernova in the Large Magellanic Cloud, a satellite galaxy 160,000 light-years away, light telescopes saw the brilliant explosion. Crucially, several underground detectors on Earth registered a brief burst of 24 neutrinos, arriving hours before the visible light reached us. Why the delay? In the final collapse of a massive star, the core crushes down into an ultra-dense neutron star. The shockwave from this collapse takes time to blast through the star's outer layers and become visible. But the neutrinos, produced in the very heart of the collapse, escape immediately, unimpeded by the overlying matter. Those 24 ghostly particles, detected from supernova 1987A, were our first direct telegram from the core of a dying star, confirming our theories of stellar death in the most dramatic way possible. They carried information about the unimaginable temperatures and densities at the moment of creation for a new neutron star, but this was just the beginning of neutrino astronomy. The quest required a detector of almost absurd scale. Enter the IceCube Neutrino Observatory, built deep within the Antarctic ice sheet. Scientists drilled 86 holes over a mile deep and lowered strings of 5,160 sensitive light detectors. The entire instrument encompasses a cubic kilometer of pristine ice. Its target is not the neutrinos themselves, but the extremely rare occasion when a neutrino collides with an atom in the ice. This collision produces a secondary particle that emits a faint blue flash of light called Cherenkov radiation, which the detectors can see. By tracing this light, scientists can determine the neutrino's energy and, most importantly, the direction it came from. In 2017, IceCube achieved a milestone. It detected a single high-energy neutrino and traced its path back to a point in the sky. Astronomers swiveled other telescopes to that coordinates and found a blazar, a monster black hole at the heart of a distant galaxy, shooting a jet of radiation directly at Earth. For the first time, we had pinpointed a specific astrophysical source of these cosmic neutrinos, opening a completely new window onto the engines of active galaxies. This ghostly messenger reveals processes hidden from traditional telescopes, where light may be trapped or obscured by dust and magnetic fields. Neutrinos give us a direct line into the particle accelerators of the universe. Furthermore, the study of neutrinos from the Sun and from nuclear reactors revealed an astonishing secret about the particles themselves. They oscillate, changing from one type or flavor to another as they travel. This strange behavior is only possible if neutrinos have a tiny amount of mass, a fact not accounted for in the original standard model of particle physics. Their ghostly nature is therefore not just a curiosity, it is a clue to physics beyond our current understanding. So the next time you feel a breeze, consider that you are also being gently showered by trillions of these cosmic messengers, each one a potential story from the heart of a star, a black hole, or the infant universe, a story we are only now learning how to read. With this new sense for the universe's most violent events, our attention turns to the ultimate question of origins, the moment when all the forces of nature were one. The cosmic web is the largest structure we will ever be part of. For centuries, galaxies seemed like isolated islands scattered across a dark sea, but modern surveys have painted a radically different picture. Projects like the Sloan Digital Sky Survey have methodically charted the positions of millions of galaxies, creating a three-dimensional map of the cosmos on a scale once thought impossible. The result is not a random scattering. It is an architecture of breathtaking grandeur, a vast cosmic web. This web is spun from great filaments of galaxies, stretching across hundreds of millions of light years, connecting at dense knots where enormous galaxy clusters reside. Between these luminous strands lie immense voids, regions of startling emptiness that can span hundreds of millions of light years, cosmic deserts where few galaxies dare to dwell. This is the skeleton of the observable universe, the end result of 13.8 billion years of gravitational storytelling. The plot began with those tiny quantum wrinkles imprinted by inflation in the universe's first fraction of a second. Over eons, gravity acted as a relentless editor, amplifying those slight density variations. Dark matter, the invisible scaffolding, provided the gravitational anchor, its pull gathering ordinary gas into its nets. Where the dark matter was densest, galaxies formed like dewdrops on a spider's web. The luminous galaxies we see today trace out the underlying dark matter framework, much like streetlights illuminating the layout of a city at night. This intricate pattern is a powerful confirmation of our entire cosmic model, from inflation to dark matter. It tells us the universe has a memory, a structure that encodes its entire history. The scale is almost impossible to internalize. A single filament in this web is so vast that our entire Milky Way galaxy would be but a single grain of sand within it. And yes, when you see visualizations of this cosmic network, it is natural to feel a strange sense of recognition. The branching patterns bear an uncanny, if superficial, resemblance to other complex networks in nature, from the branching of neurons in a human brain to the root systems of a forest or the structure of the internet. This is not a sign of some mystical connection, but a fascinating demonstration of how universal mathematical principles of growth and connection can manifest in vastly different systems, from the quantum to the cosmic. To see this map is to understand that we are not just living in a galaxy, we are living within a single thread of an immeasurable tapestry, a tapestry whose pattern was woven in the first instance of time. This grand architecture, however, is not the final word on structure. It raises a profound question about our own place within it. If the cosmos is a web of such immense scale and age, what does that imply about the possibility of other threads holding worlds like our own? For hundreds of millions of years after the Big Bang, the cosmos was a formless sea of darkness. This was the cosmic dark ages, a time when the universe had cooled from its initial fireball, but no stars yet existed to pierce the gloom. It was filled with a thick fog of neutral hydrogen gas, atoms that readily absorbed the energetic ultraviolet light that would try to pass through them. The universe was opaque, a vast and silent shadow, Then a few pinpricks of light began to flicker on. The very first stars, known as population 3 stars, were likely behemoths, hundreds of times more massive than our Sun. They lived fast and died young, burning with a fierce, hot blue intensity. Their ultraviolet radiation acted like a cosmic blowtorch, striking the surrounding hydrogen fog and stripping electrons from the atoms in a process called ionization. An ionized atom cannot absorb that same ultraviolet light, so the radiation could now travel farther. One by one, then in growing numbers, these first stars and the earliest galaxies and quasars began to create bubbles of clear, transparent space within the neutral fog. Over several 100 million years, these bubbles grew, overlapped, and eventually filled the entire observable universe. This great transformation is called the Epoch of Reionization, and it marks the moment the cosmic fog lifted forever. We know this happened because our most powerful telescopes, when they peer at the most distant quasars, see something telling in their light. The light from these brilliant, ancient objects shows a distinctive absorption pattern, a forest of dark lines caused by the last remaining patches of neutral hydrogen that had not yet been ionized. The more distant the quasar, and thus the further back in time we look, the thicker this forest becomes until eventually, beyond a certain point, the light is completely blocked. That point is the edge of the reionization epoch, the final wall of the cosmic dark ages. Studying this era is one of the primary missions of the James Webb Space Telescope. By looking for the faint, reddened glow of the very first galaxies, Webb is acting as a time machine, capturing the moment these cosmic pioneers were actively burning away the primordial haze. It is a search for the architects of the clear cosmic ocean we now sail through. This was not a gentle sunrise, but a dramatic and uneven clearing, a patchwork of light fighting its way through a global fog. How does it feel to know that the very transparency of space, the fact that we can see galaxies billions of light years away, is a gift from those first, short-lived generations of stars? Their brilliant sacrifice ended the universal night and set the stage for everything that followed, from the majestic spiral galaxies to the gentle starlight that eventually nurtured life on a small, rocky world. The most distant stars do not just shine more faintly, they seem to think more slowly. When astronomers train their most powerful telescopes on the cataclysmic explosions of white dwarf stars in galaxies billions of light years away, they witness a strange cosmic lethargy. The supernova there, the brilliant type won a standard candles we use to measure cosmic expansion, unfold in a peculiar slow motion. Their brightening and fading takes measurably longer than identical explosions in galaxies closer to us. This is not an illusion of distance or a trick of the light. It is cosmological time dilation, a direct and stunning consequence of living in an expanding universe where space-time itself is the stage and the clock. Imagine you are watching a film of a distant supernova. The film was recorded on a camera in that far-off galaxy, but the projector showing it to you is here on Earth, and the projector is running on a power source tied to the stretching of space. Because the universe has expanded in the time it took the light from that explosion to reach us, the very fabric carrying that light has been stretched. This stretches the wavelength of the light, causing the redshift we measure, but it also stretches the timeline of the events we observe. Every tick of the clock in that distant galaxy, every second of the supernova's brightening, is delivered to us over a longer interval of time. It is as if we are watching the universes pass through a temporal magnifying glass. This effect is distinct from the more familiar time dilation predicted by Einstein's special relativity, which occurs when objects move at speeds close to light relative to an observer. That is kinematic time dilation. Cosmological time dilation is something grander, a slowing dictated not by relative motion through space, but by the expansion of space itself. It is a signature woven into the fabric of the cosmos. When we measure this slowing in the light curves of ancient supernova, we are conducting a direct test of our cosmological models. The amount of time dilation we observe must precisely match what general relativity predicts for an expanding universe with a specific history of dark energy and dark matter. So far, the observations fit beautifully, providing yet another independent pillar of evidence for our current picture of cosmic evolution. To look deep into space is to look back in time, but we now understand that we are not just looking back. We are looking at a past that is literally running slower. The universe preserves its youth for us not as a frozen snapshot, but as a slow-motion replay, allowing us to study the fiery deaths of ancient stars with a patient, drawn-out clarity. What does this mean for our perception of reality? It means that when we point our telescopes at the edge of the observable universe, we are not merely receiving old light. We are interacting with a different flow of time, a rhythm set when the cosmos was young and space was tight. The universe itself is the ultimate time machine, and it shows us its childhood moving at a dreamlike pace, a constant reminder that we are not observing space and time separately, but a single, dynamic entity called spacetime. The universe's childhood album just received its sharpest pictures. The James Webb Space Telescope, positioned 1 million miles from Earth, has opened its infrared eyes to the cosmos, and the first snapshots are rewriting chapters of cosmic history we thought were settled. Its primary mission is to see the first light that ended the cosmic dark ages, but in doing so, it has found galaxies that seem to defy the timeline. These incredibly distant smudges of red light, seen as they were just a few 100 million years after the Big Bang, are not the faint, fragile infant structures astronomers expected. They appear massive, mature, and already brimming with stars. Finding such developed galaxies so early is like opening a family photo album and discovering a fully grown adult in a picture labeled first birthday. This has sent theorists back to their drawing boards, questioning how dark matter halos could have gathered ordinary matter and forged stars with such astonishing speed. Perhaps the first stars formed in sudden, explosive bursts, or maybe our understanding of galaxy formation in those initial epochs is missing a crucial piece of physics. Webb is not just a camera, it is a chemist. By splitting the faint light from these ancient galaxies into a spectrum, it can detect the chemical fingerprints of specific elements. Already, it has identified carbon and oxygen in galaxies observed when the universe was only 350 million years old. These heavy elements are forged in the hearts of stars and scattered by their explosive deaths, meaning entire generations of stars must have already lived and died in what we thought was the universe's earliest childhood. This forces a profound compression of the cosmic timeline, suggesting the first stars ignited even earlier than our best models predicted. Closer to home, Webb is revolutionizing the study of exoplanet atmospheres. As a planet transits its star, Webb analyzes the starlight filtering through that alien air, identifying molecules like water vapor, methane, and carbon dioxide with unprecedented precision. For small, rocky worlds, this is our first step toward detecting potential biosignatures, combinations of gases that might hint at biological processes. It is turning distant points of light into places with weather, chemistry, and perhaps one day, signs of a habitable environment. Furthermore, its infrared vision pierces the dusty veils of stellar nurseries within our own galaxy, revealing hundreds of previously hidden newborn stars and the intricate structures of planet-forming disks in stunning, tapestry-like detail. Each of these early revelations carries a deeper lesson about discovery itself. The James Webb Space Telescope was built with specific questions in mind, yet its greatest gift may be the questions we never thought to ask. It embodies a fundamental truth of science that every new window onto the universe does not just provide clearer answers, it reveals a deeper, more complex reality than our theories had imagined. Our current story of cosmic evolution is being stress-tested in real time. What other foundational ideas might shift in the next decade as this telescope continues its silent watch? We are witnessing not an end to discovery, but a thrilling new beginning, a reminder that our view of the cosmos is always a draft, awaiting the next line written by the light of ancient suns. The fundamental laws of physics are written with numbers of breathtaking precision. The strength of gravity, the mass of an electron, the energy inherent to empty space, these are not arbitrary figures. They are the universe's fixed settings, and if any one of them were altered by even a razor-thin margin, the story of everything would be rewritten into a silent, sterile void. If gravity were slightly stronger, stars would burn their fuel too quickly and collapse, never lasting long enough for planets to form or life to evolve. If the nuclear force that binds atomic nuclei were a fraction weaker, hydrogen, the simplest element, would never fuse into helium, and the furnaces of stars would never ignite. The cosmos would be a cold, dark expanse of unlit gas. This exquisite balance is known as the fine-tuning of the universe. It presents a question that sits at the very edge of science and philosophy. Why does reality appear so perfectly calibrated for our existence? One compelling answer is offered by the anthropic principle, a simple yet profound logical statement. It suggests that the universe we observe must be compatible with the existence of observers because we are here to observe it. In other words, we could not possibly find ourselves in a universe where the constants of nature did not allow for stars, planets, and carbon-based life. Our observation selects for a universe that permits observers. This is not an explanation for why the constants are what they are, but rather a recognition of a necessary condition for our own inquiry. It shifts the question from why is the universe fit for life to what does it mean that we find ourselves in a universe that is. This line of thinking leads to one of the most expansive ideas in modern cosmology, the multiverse. If our universe is just one bubble in an eternally inflating cosmic foam, as some interpretations of inflation suggest, then each bubble universe could have its own random set of physical constants and laws. In this vast, perhaps infinite, ensemble of universes, most would be stillborn or barren, their numbers set to values that prevent complexity. But by sheer chance in a tiny fraction of them, the numbers would line up just right. We, of course, would find ourselves in one of those rare, habitable bubbles, simply because we could not exist anywhere else. The multiverse offers a naturalistic explanation for fine-tuning, removing the need for a single, uniquely designed cosmos by invoking a statistical landscape where every possibility is realized somewhere. This idea forces a deep and humbling perspective. It suggests our entire cosmic history, from the Big Bang to the rise of consciousness, may be a local event within a much vaster, stranger meta-reality we may never directly access. It blurs the line between physics and philosophy, between empirical science and metaphysical possibility. Are we the product of a profound, underlying purpose, or the beneficiaries of an immense cosmic lottery? The debate continues not with telescopes, but with the rigorous tools of mathematics and probability. To stand at the end of this journey through 25 discoveries is to see a universe transformed. We began at the center of a small, celestial sphere and have traveled to the edge of an inflating multiverse. Each breakthrough was a step out of a comforting cave and into a colder, grander, and more magnificent light. We learned we are not the center, that space is growing, that the cosmos had a beginning, and that most of it is made of substances we cannot see. We heard spacetime ring with the collision of black holes and found the letters of life's alphabet written in the dust of comets. The universe is not just stranger than we imagined, it is stranger than we can imagine, yet through patience, curiosity, and courage, we have imagined quite a lot. Our view has changed forever, not because we found final answers, but because we learned how to ask better questions. And somewhere in the silent dark between the stars, new questions are waiting. These threads are not separate. They weave together into a single, breathtaking story. The quantum fluctuations stretched by inflation became the seeds for galaxies, whose starlight forged the carbon in our bones. The same gravity that guides planets sculpted the cosmic web, and the dark energy now accelerating its expansion will one day dictate its final fate. This is the true revelation of our journey. Science is not a collection of disconnected facts, but a cumulative, self-correcting story. Each discovery, from Copernicus moving the Earth to Webb finding impossibly early galaxies, was a correction to the draft, a deeper layer of understanding added not by discarding the old but by building upon it. The static celestial sphere gave way to a heliocentric system, which demanded Kepler's ellipses, which cried out for Newton's gravity, which required Einstein's curved spacetime, which predicted black holes and gravitational waves we can now hear. Every answer has been a threshold, not a destination, each one opening a door to a room filled with even more profound questions. We began this journey believing we stood at the center of a small, illuminated stage. We now find ourselves conscious participants in a dynamic, evolving, and almost unimaginably vast reality, a reality we are only beginning to comprehend. Our view has changed forever, not because we have solved the cosmos, but because we have learned to see it as a whole, interconnected mystery of which we are an intimate part. This integrated story leaves us with a final, humbling reflection. If we are the universe's way of understanding itself, what does it intend to understand next? The story we have traced is a single, unbroken thread of wonder. From the moment Copernicus relocated our world from the cosmic center to the instant we heard black holes collide, these 25 discoveries are not isolated facts. They are chapters in a single, grand narrative of awakening. We have journeyed from a small, human-centered stage to a dynamic, evolving reality where we are not the protagonists, but a conscious, fleeting expression of its deepest laws. This is the profound and humbling shift at the heart of our exploration. The universe was not crafted for us, yet we are here, crafted from it, and able to trace its epic from the first quantum whisper to the vast cosmic web. The key takeaway is not a list of answers, but a recognition of a beautiful, perpetual incompleteness. Every mystery we solve, whether the nature of dark matter or the trigger of cosmic inflation, does not close a book. It opens a door to a room filled with even more profound questions. As the astronomer Edwin Hubble once reflected, the history of astronomy is a history of receding horizons. Each new vista reveals a landscape vaster and more mysterious than the last. Let this journey ignite your own curiosity. The next time you look up at the night sky, see it not as a static ceiling adorned with distant lights, but as a living window into an epoch that is still unfolding. We invite you to share in the comments which single discovery most reshaped your own perspective on our place in the cosmos. For more journeys to the very edge of understanding, subscribe and join our continuing exploration. And hold this final thought close: the greatest discoveries that will forever change our view of the universe are almost certainly still ahead of us, waiting in the silent dark